I'm Michael. I founded Q.ANT in 2018, 7 years ago. What we are building are AI accelerators. We just managed to outperform Intel. All our chips are produced in Europe, and we are integrated into more than one, let's call it several data centers in Europe already. If I get the slides, can you explain how we did this? And by the way, thanks for all who are now re-queued to give me the slot here.
Now we start talking.
Oh, we can also talk.
we just talk about it.
Absolutely.
Yeah, it's a wilder session, right? So I think let's start with one big topic, or with sort of maybe even the elephant in the room, right? You know, we speak a lot about AI sovereignty, autonomy, agents, etc. But ultimately, our biggest problem in Europe is energy and access to energy. And I think, Michael, you could have one of the breakthrough technologies for Europe.
This was the perfect bridge.
Is that a good bridge? Here you go.
Also working? I guess so. So, fantastic. I prepped for a little game. So we all like to use AI, but the question is, what are we using it for? And are we aware of the consequences? And that's the interactive part. The first question is, do you know this action figure game? Typing something into OpenAI's ChatGPT and you get basically your personalized action figure as a picture back. Who participated into this? This is the active part of my presentation. Okay, not so many. You don't be shy, I did it as well. You need to know what you're talking about. So the main question about is, what would you judge? How long does it take these gigantic graphic cards that we adore so much to compute on such a picture? Is it, and we just do it by hand raising, is it 0.5 seconds? Is it 2 seconds? First hand's getting up. Is it 10 seconds? Wow, did you listen to this speech? Before, it is 10 seconds, and it's not because of they're stupid. It's because of that this technology can't do any better. It's because of that the CMOS technology, that it is at the heart of these graphic cards, is procrastinating. If you compare from any vendor that you love or don't like or like, I don't actually care. The way these chips are designed since the 1970s forbids you to be faster. We've basically hitting the boundaries of physically possibility. That's on this chart. The performance does no longer grow. The only thing that grows effectively is the size of the chips. The elements, actually, all of these chips are manufactured on 3-nanometer node technology. So there is no speed up. The speed up comes by increasing the size. Now what happens when the size increases? That's the second question. What would you assume is the energy consumption per picture that's going to be used for one? And I did this in terms of recharging your smartphone. Who believes that one picture takes 20% of the capacity of your battery in your smartphone? Raise your hand now. 1, 2, 3, 4, get a 5, 6, no. 50%. Maybe we are not so, it's delicate, this topic. Is it 100%? Some of the things thinking, it's 100%. And it's not so much, it's 20 watt. But if you think about it, per day in the hype phase, more than 30 million pictures have been generated. This agglomerates to the energy of a small city. This was used just to provide action figures to us. So when we go to the fundamentals, we obviously see that AI and all that we love about AI is putting and hitting physical walls. Now, the third aspect, and this comes more on a European perspective, okay, That's energy is rising. From the year, so that's the forecast. And go wherever, I mean, when we prep for this interview, when you think about if all these chips that have currently been announced to be rolled out into the market, the energy consumption is
2% of the worldwide available energy.
So the stock market value of NVIDIA anticipating the number of chips being shipped to the market is equivalent to 2% of the world's energy consumption. Oh. Okay. And the third aspect is, from a European point of view, we can dream about AI. But if we're not getting the hand on the full stack, we can dream on. We have nothing to tell in that race. The IP of the chip is in the US. The production is in Taiwan. The processors are shipped to the market from the US. The software stack is defined from a US company. And the only thing that they're asking you for is your data. That's it. So if we really want to talk about sovereignty, we have to take it from the scratch. We have to think it from the core, from the bottom to the top. And this is what we did when we started Quant. We not just replaced the graphic card and thought, yes, we do a bit of better graphic card. We fundamentally disrupted this by replacing the compute core from electricity to light. And that changed everything. Because of light, we've been able to build our first pilot line in Europe, in Stuttgart. We're producing the chips of our processors in Europe. How is this possible? Because light does not need these ultra-small dimensional structural elements as you see them in the scaling law of the CMOS world. They can work on foundries that have been state-of-the-art in the 1990s. And we repurposed one of these foundries to serve as our pilot line for our first revolution. And with this, we demonstrated that we can build a full processor. That's what you see on the right. And to the experts in the room, it looks like a PCI Express card. It looks like a graphic card. It feels like a graphic card. You can plug it into your compute stack. The only thing that you're going to miss are the liquid cooling elements. And we didn't forget them, because light does not heat up the chip. The card that Isabeau is holding in her hands here has an energy consumption of 40 watt. A comparative graphic card would consume round about 1 kilowatt. That's the energy your oven in your kitchen consumes. Think about this. This card is 30 times more energy efficient just because we replaced electricity for light. We deployed first service systems here in Munich. In the meanwhile, we have more installation across Europe. And I mean, we should ask the customer what they think about it. We learned that they're very happy because the integration into the data center was exactly as exciting as it was not. Plug it in, turn it on, let it work. What the difference is, and this is a bit of the technological tricky story, we unveiled our second generation on last November. Currently, we are focusing on physical AI, on pictures, audio, video. Now, when you think about what the job of such a machine is, you have a neural network that you're training with a machine, and then you type in, please recreate a picture. So if we consider the left picture, the wood, to be the ground truth, that's what you actually want to return. We competed on the same board with an Intel CPU of the latest generation. And just without going to the numbers, you can see that our picture has a much stronger clarity than what the CMOS could accomplish within 400 cycles. That's because of light also computes fundamentally different. It removes a lot of data movements on the fundamental layer and opens ways to complete new algorithms. And that's the essence. We could regenerate from a neural network pictures at a higher quality, at a fraction of the data and the energy. Everything fully integrated into the existing compute stack, built in Europe. What we can't change is your user habit. You're going to use this tomorrow again. And I'm not the person who is about forbidding things. But we should react with technology on such trends, and we should not repeat what we've done in the past. Because if you repeat what has been the success story of the last 40 years, we are getting exactly what we got the last 40 years. And that's clear. These scaling laws are approved, and we know them. And they're ending up in a lot of energy consumption. For me, if we go to reality check, the future compute system will consist of a multiple dimensional chip architecture. There will be the CPU, there will be the GPU, but there have to be additional workers, tools in the compute stack to take on specific tasks. And from a European perspective, please don't even dream about that we can contribute to the CPU or the GPU. That race has begun 30 or 40 years in the past, and it's super unlikely that we're jumping on the train. Our focus should be on something new, on something that we can add to this compute stack, and that's changing it fundamentally. And there I see photonic computing as one of the great challenges for us, but great opportunities for Europe, because we've demonstrated that we can add this type of processors to the compute stack from a European perspective. That's the way we can go. Maybe it's a one-time life chance of every one of us that we can start a true revolution in that industry. And with this, I'm at the end, and I think there's...
Let's have a conversation about it. This sounds like one of the breakthrough technologies, right, for Europe. How, when you compare us with the rest of the world, where do we stand from a development perspective? Because in semiconductors, at least when I was in tech banking 20 years ago, it was so important that you are ahead of the curve, right? Because there was no way you can catch up. Has that changed, or is this still true? And then the second question is, where are we here in Europe, or you specifically?
On this particular technology, we're leading in the world. So we consider our advances or our competitive gap to round about 2 to 3 years. The reason for this is we took it fundamentally different than all our competitors, even from the US. What you've seen and sounded so simple, pilot line and so on and so forth, underneath there is a lot of thorough engineering. For instance, we developed our own chip material. We just didn't say, yes, let's use silicon because it's available in any foundry of the world and let's go with the compromises. We took it very thorough. We understood what light is needing, and we developed a material system that basically features light and not just presses it into old structures. Yeah, yeah. I'm blushing. Now, what should I say since I was born in Munich? Okay. The second thing, but maybe coming more to the technological aspect, what led us then to become so far ahead of the international competitor was that we also understood that on the fundamental photonic layer, there shouldn't be any kind of electricity. That was also part of this material stack. Now, what we can do is we can control the full light without a single piece of electricity on the photonic layer. And what does this mean? And this is where all the competitors effectively were struggling. We are the only company that can provide the computational accuracy that's needed to execute on AI tasks. All the others that have tried to use photonics because it sounds very simple, use light instead of electronics and so on, they're struggling to get the computational precision out of the circuit, and in the end, they use less energy, but the result of the computation is also very strange. This actually was the match.
And a related question, obviously, your name, your company name is Quant, right? But this has nothing to do with quantum computing. Can you just, maybe, get everything in order, right? So the current compute technology, what you do, the photonics, and quantum computing.
So thanks. Yeah. So first, in the meanwhile, the name is often associated with quantum. Actually, when we started, the brand agency told us use 4 characters because then you can type it fast into a keyboard. And then we said, okay, let's take our values that we're sticking to. It was team, anticipation, novelty, and quality. And we flipped it around, and then there was quant. We put a dot in the middle because then we could trademark that. And this is when we started in 2018. Back then, quantum was not so broad, and we've also been among only a very few companies with a Q as a starting character. In the meanwhile, things have changed, but we still are not doing quantum computing. Coming to the technological aspects, what we are doing is analog computing. On a fundamental level, the great thing about light is that you don't need to think in zeros and ones. You're not thinking in bit flips. Now, what's the advantage here is the following. Think about you want to compute something. In the end, the only response a digital circuit can give you is 0 or 1. It's a linearized function. So everything you want to do in the end is broken down to zeros and ones. And we are computing in waves. The best example I can give you, if you want to get a computer to draw a circle, depending on how accurate you want to draw the circle, you need a very large number of data points. A lot of data points mean a lot of data pushing, and in the end, you can only approximate the circle. We have a sine function natively integrated into our compute stack. You need 2 parameters to describe the full circle. Accurate. You can't be more accurate than this function. And that's where we save a lot of energy. This is where we are. Now, the differentiator to quantum is the following. Quantum computers have quantum effects. This is what we don't have. And if your computation requires quantum effects, use a quantum computer. If you are advanced on math, use our computer. If you want to go on your email client, use a CPU.
As simple as it is, right? But what we spoke about, Michael, and I think this is important because at the end of the day, we think about sort of what are the frontier technologies, right? And what are the breakthrough technologies for Europe. You could use your chips and your technology also for to power quantum computers, right? That's correct. That's correct. All right. We have only 1 minute left. We don't want to add to the delay. So, Michael, thank you so much. And I can only encourage everyone to, every time we speak about sort of AI sovereignty, and compute power and energy in Europe, think about photonics. Thank you so much.